Yes, it's good time to start right now. I see recording in progress. Yes.
Okay. All right. Cool. Hi everyone. Thanks for joining today, Saturday, September 7th. Want to talk Eastern Time.
What happened?
It looks like
Loading.
Young is offline. There you go.
Sorry.
I think Young was offline a little bit. Maybe the network was down a little bit. So let's start it again.
Oh, can you hear me? Eric, can you hear me?
I can hear you, but there's something in front of my screen, and I don't know if my screen is being shared.
Um,
Yes, I can see your screen. Yes, I can see your screen all the time.
okay. Well, okay, that's weird. Okay. Well, if people can hear me now, I guess I can just start again really quick. Um, yes, I don't know why the audio cut off there. Sorry about that. But yeah, really quick, another quantum computing meetup today. Thanks for everyone for joining. Today we have Eric Reeder. Today's topic will be a critical history of quantum mechanics. Many themes in physics will be discussed today, such as photon model, loading theory, Compton effect, Schroedinger, response time arguments, light detectors, beam split coincidence tests, matter wave tests, EPR-Bell threshold model. Here are the lecture slides that was included in the description. If anyone wants to take a look right now, this will be covered today. Yeah, it's basically like today will just be a big discussion on the history of QM, consistence for arguments for and against QM.
Right.
Yeah, and yeah, really quick, Eric Reeder, lifelong independent researcher and inventor, studied physics at California State University.
Right.
He published papers including those in progress in physics, physics essays, and 2015 SPIE water photons conference proceedings.
Right.
I'm also including some links to his experiments, and his writing is posted on this website here. Cool. Well, anyways, without further ado, Eric Reeder. There you go.
Thank you. Very
Yeah.
nice introduction. Thank you, Young. Thank you, Helen Ma. Right. The lecture slides are hopefully viewed afterwards. There's way more detail on the lecture slides than what I can talk about. So if you haven't figured before, in my previous lecture, what I did was experiments with the beam split coincidence test, but I do it with gamma rays, and we'll be comparing how they do it and I do it. And you already went through my overview of the history, and that I'll be explaining in order of these themes instead of the chronological order. Um, can you see my mouse on the screen? Is the whole screen being shared? I cannot see it.
Yes, yeah. Right now it says a particle model often
Yeah.
works. Yeah,
Okay.
97.
Good. Right. So the great J.J. Thomson did the experiment to show the charge to mass ratio of the electron, and he assumed the particle model in free space. And very soon after, his associate, Mr. Townsend, and also JJ, they balanced liquid drops to see the charge constant independently, but this was in bulk matter. And so I'll be pointing out that it makes a difference how you look for the charge constant, whether it's in matter, in bulk, or in free space. And you can see in my theory later, I'll explain it's possible to understand that the charge is a maximum, that it's a threshold, and that it's not quantized as assumed in this pair of experiments. It's sort of set the stage for seeing everything as particles. So it's important to understand in Planck's 1900 famous paper on the equation for the black body distribution that Planck did his constant times frequency as a energy in matter, not light. And many books and papers will say that Planck quantized light. Well, it's possible to do it both ways, to do that derivation, to see it as a property of matter or light at this stage compared to that data of the black body. But Planck did it most importantly here as a property of matter. So you can read my markup to convince yourself. Soon after, Lenard did the important experiment to show the photoelectric effect property that he didn't quite do the proportionality between frequency and escape energy of the electron, but he did understand that the frequency mattered because he put filters in front of his light source that was mostly ultraviolet, cut out the ultraviolet, and saw that the frequency mattered. And so Einstein got a hold of this, and I think what happened is that Einstein's wife worked with Lenard. There are accounts of that. And so he knew about Lenard's work. He quoted Lenard, and Planck quoted Einstein quoted Planck, but Einstein derived his E equals h nu in his own way. And and then he used E equals h nu in a particle model to equate to the kinetic energy 1/2 mv squared of an electron that would escape, which was pretty cool. And others found that it worked. But he really meant it, that light was like a particle, that it does not divide, it only produced and absorbed in complete units. So this has been accepted by mainstream, and I'm going to show that this is not true, but we'll see. We'll see what happens here. So right away, many great people, Lorentz, paraphrasing, light quanta just won't do. And so JJ and O.J. Richardson, Sommerfeld, Debye, Millikin, they all objected to this particle of light kind of model because obviously there's the wave properties, and it's just, how do you explain the wave and interference with particles? They understood that you cannot do it. So not too long after, there's the Bohr-Einstein debates, and it's written up in Bohr's book. And this is a really great sentence. It's like quantum mechanics in one sentence, and I'll read it. If a semi-reflecting mirror is placed in the way of a photon, leaving two possibilities for its direction of propagation, the photon may either be recorded on one and only one of two photographic plates situated at great distances in the two directions in question, or else we may, by replacing the plates by mirrors, observe effects exhibiting an interference between the two reflected wave trains. Okay, so there's the particle part and the wave part clearly explained, and they say that the visualization of this is impossible. So straight away, it's about a model, that the photon idea is a model, not a thing. It's way easier to understand and not be confused, to take it as a model and not describe light by a thing like going across space. However, many experiments have been shown that this model works. So we'll look at that. So experimentally, it's done like this, where there's a singly h nu source, Planck's constant times frequency, and there are all these different ways that people figure, well, how is it that it's a one at a time source? So they see in a coincidence experiment, they look at the pulses from these detectors and they see that they're out of time. And then they say things like it's all or nothing, it goes like a photon. This is the particle part. And then you rearrange the beam, and this way it has to be both ways in contradiction to the one way or the other in order to see the interference pattern. And everybody knows that, except what happened is they interpret this as a probability wave. So yeah, we're going to show that it's this part of the model that breaks down in my experiments. So many great people wrote about this, they understood, and Heisenberg writes about, from the first part of the photon model, about the reduction of the wave packet that implies entanglement and the measurement problem, and all these ways of understanding quantum mechanics. These are all pretty much the same thing, the quantum weirdness. But absent any workable alternative, we've heard of all these interpretations like many worlds, and we're all in a computer simulation, all kinds of stuff. And so to me, these are acts of desperation. But this is where the problem of quantum mechanics has led to. So also de Broglie wrote about in his book the model of the one way or the other and the interference. So they understood that. So then Millikan did, and some others also tested the photoelectric effect equation and to see if that was true about the photoelectric effect. So Millikan agreed with the equation. That's good enough. But he argued against the photon model, and he explored the loading theory, and he coined the term, I'll show you, of the loading theory. But there's this way of thinking about the experiments that I want to point out. In the title, A Direct Photoelectric Determination of Planck's H, well, it's not direct. The equation generates the H to E ratio. That's the message of the experiment, is the H to E ratio. So when you borrow a constant like E and put it in, it affects how you're thinking about what goes on. So I'll point out this ratio idea later in my theory. It's an important idea. So I hope you can see the whole screen here, because I can't. There's something in the way.
Yeah, we can see it.
All right. So I build upon Planck's second theory. Planck had a second theory of 1911. And he had his constant as not a quantization, it was a threshold. And also, again, H is a property of matter, not light. And so he had this drawing in his papers of how absorption energy in his oscillators would load up and then suddenly emit an H nu of light. And so in the equations he uses, you can see that H is expressing a maximum. It's not a quantum of action. So he had that pretty clearly, but it's a obscure paper. It's in German. The translation of this paper is in my work on my website. I'm the only one it looks like that has translated it. So our experiments mostly see these discontinuities, and it's hard to see what goes on here before there's an emission from, let's say, a atomic emission of light. Another important thing that came out of this derivation of the black body equation, all this is about his derivation of the black body equation. So what came out was this half an h nu, and that has been used in low temperature physics. And I embrace this. It's the average amount during the loading. There's a preloaded state whose average has this amount of energy. So other great physicists explored this idea about a loading up of kinetic energy in the electron, and that there's a but it was a continuous kind of loading. And it's not quite a workable loading theory when you compare to experiments when you take this detail of continuous loading. So we'll point that out. So Millikin, in his exploration of the photoelectric effect and what kind of thing was going on about, he talked about that energy could be stored up from light of whatever wavelength, and it needed but a minute addition. The minute addition idea, that's what makes it understandable, a loading theory. A workable loading theory would have this minute addition property where that's all it would need to set it off to see a detection event. So anyway, he calls it the loading theory, and it's a property of the electron. But in his next book, he explains the same idea of the minute addition, but he gives up on it. He says very difficult to conceive. And but I say it's not so difficult to conceive. Even a classical oscillator can maintain a frequency and some threshold amplitude, and you pump more energy into it, and then it could become unstable. I've even seen that in my experiments with musical instruments. And that's partly how I figured this out from my work with music. But this is the last place that I could find, I don't think you'll find anywhere, where there's a discussion of a workable loading theory. It seems to have been forgotten in our literature. So to review, these are the models of absorption and emission of light. Planck's first theory, it's been taken on as quantized absorption, quantized emission. His second theory, continuous constant absorption, quantized emission. And then this modification by Millikan, which is the one I build upon, where there can be an arbitrary way that the light can absorb and have some preloaded state, and then it shows up emitted quantized. And so I'm going to call this the threshold model to this version of the loading theory that I developed. So I call the threshold model. So in the meanwhile, there's the Compton effect that had the particle model used as the derivation of the equation for this effect. And it seemed to work really nicely. Also, Debye developed this particle derivation. So people use it as evidence that energy conservation needed to be seen in terms of quantization itself. And I show some of that argument. Then there were other people who looked at this. The Bohr, Kramer, Slater considered that it doesn't have to be by particles, that there's a statistical, more classical way, but his model did not predict coincidences in the experiments. So when Bothe and Gauger did the experiment with X-rays and charge detectors, they did see some level of coincidences, but how much of a coincidence, it's really ambiguous as to what kind of model it predicted, but it was more than accidental chance is what happened. And so then Bohr and friends gave up on his earlier statistical model, and it just went that way where everyone was thinking in terms of particles. And then the Compton and Simon experiment, it looked like it was coincidences, but just how much and whether it's an average or each or one-to-one property, it's pretty ambiguous when you try to look and see what they did. But the literature and our books pretty much followed the idea that light was quantized after these experiments. I'm going to return to the Compton effect later. So, but in the meanwhile, there's a wave interpretation, a wave derivation of the same equation in Compton's book that uses Bragg diffraction and the Doppler shift. And you don't need to have the particle model to come up with the equation for explaining the Compton effect. But it was pretty much forgotten. But it's in Compton's book of all places. And I worked on this and I adjusted his model, pretty much used the same equations, and I make it more acceptable as to the assumptions behind the model that's going on here. That's to be explained like in a future lecture, how I derived these other, the effects like the Compton effect and so on. But what's important is they had the right equations in the derivation and came up with the right equation to match experiment by waves. So, and so in the meanwhile, looking back, de Broglie had his wavelength equation, and the experiments seemed to they did justify this equation. But the derivation, I will argue about every step of the way as to what's going on with his derivation. Most importantly is that there's this c-squared equation that was sucked out of special relativity to have a velocity that's faster than the speed of light. And various books have looked at that and said, oh, that's evidence of a probability interpretation to go with the de Broglie equation. So soon after, G.P. Thompson and Davison and Germer measured charge diffraction, and it was pretty disturbing. Well, how can it be that we have a wave effect and it's about particles and what's going on? So here's where Thompson coined the term ghost waves in his book. So they were trying to figure it out. So Schrodinger, he had this great equation, but what I say is really the most interesting thing about Schrodinger's work is that he understood that the envelope of his wave function, and when you square it, you get beats. And it's the beats that are the interaction between light and charge. The envelope of psi is the identity of charge. And I embrace this model and build upon it. But soon, Born introduced a probability interpretation of the wave function, but Schrodinger hated it. I'm opposed to the whole bunch of it. He explains real clearly in his later book that he argues against Born's probability interpretation. So let's go back to the element of time, the response time arguments in the photoelectric effect and the Compton effect. So there are short time response time arguments that have been used to argue against any loading theory. And so you'll see this in our textbooks where they'll quote, very often they'll quote Lawrence and Beam's paper. But again, they compare to this continuous absorption model and don't know anything about this possibility of a preloaded state. So in all of our textbooks, when they compare this, and I put them here for your reading later, about what's in famous books from famous people and in our textbooks, and all the rest of the textbooks do this to show as an example that by just looking at the time response in the photoelectric effect, they say it's impossible for any loading theory to be workable. But like I'm saying, they're comparing to an unworkable kind of loading theory. This has convinced physicists and students to give up on this idea. This all throughout our textbooks, these homework problems. So again, back to the Compton effect and the element of time, they look at the amount of time it takes for the pair of X-ray electron or gamma ray electron pair events. And they keep doing it over, and they keep getting faster and faster response times. They're only looking at the quickest response time, the shortest response time. And there are longer times, and that's important to understand what goes on. But they're only examining these shorter response times and trying to say that it has to be like photons and particles because of the short response times. They're comparing again to a non-workable loading theory. So there is all this wave particle confusion, and I like looking at Feynman for that. So here he is trying to explain wave particle duality with electron diffraction or whatever, particle diffraction. Diffraction of particles. Let's get it straight. Particles do not diffract. If you're going to teach this, please at least call it a quantum mechanical particle. So even in the context of where we've been exposed to this idea, it's best to say quantum particles instead of just particles. So we can set the stage for like, well, maybe there's something else going on here, that it's not particles going through guided by a probability wave, which is a ghost wave. And like, what is that? So there are other things wrong that are in his writing. So he doubles down on this idea. It's like particles. It's not like particles. That's throwing away the wave properties. And this is a critical history of quantum mechanics. I'm being critical. It's not like particles. You're not going to throw away all the wave properties in front of me and a bunch of other people. I'm not alone. Then there's no splitting of light into half particles. Well, what he really meant was that Planck's constant doesn't split, because there are all these other ways of doing splitting with Raman and Compton scattering and parametric down conversion, whatever, and you lower the frequency. So that was pretty confusing. Then this is just completely wrong. He looks at the clicks in a photomultiplier tube and says, clicks of uniform loudness are heard. It's just not true. We're going to look at the photomultiplier tube and see that in a moment. And then there's this idea of all or nothing. Well, that's how it's been accepted there, but we're going to examine whether that's true or not. All right, next slide. Here's the distribution of pulse heights from a photomultiplier tube from monochromatic light. And I've done this test. And so it's in the a photomultiplier data book. And what happens is when people use the photomultiplier, and this is for any detector, even if it's cooled by liquid nitrogen or avalanche photodiodes, whatever, they all have this wide distribution of pulse height. On the horizontal, it's pulse height. So if you were to eliminate the smaller pulses, then you're throwing away so much data where one can argue that it'll be against seeing the possibility of a 2-for-1 effect, as I call it, where you can split a H nu to go to 2 detectors to see, well, is it 2? You start with 1, and do you get 2? That's what the experiment is. Starting with 1 at a time, seeing if you get 2. Well, can you do it with this kind of detector? I say no. They have to throw out, they all have pulse height filters where, and they don't say where they set, nobody says where is it that they throw out these smaller pulses, all this noise. It's very suspicious that they don't talk about where they set the discriminator level. I show everything in my data. There's way more to see in my experiments than you'll see from anyone else's experiment. Anyway, there's this problem using photomultipliers, but you do not have the problem with gamma rays. You have pulse height resolution. On the horizontal of the graph, pulse height is proportional to the electromagnetic frequency, and it's proportional to the H nu energy of detection. Energy, H nu is still correct, but I'm saying to put it in the energy of detection and not the energy of a photon. Say, please, if you're going to say it's a photon, you've explained in the wrong order. All of these experiments are about, is it a photon or not? So if you use gamma rays, you don't have that pulse height resolution problem. And also, very important, you get to do a much better test to see if your source is 1 at a time to start with as it goes to the beam splitter. I'll explain that later. So we're going to look at the tests that have been done in the history to see the beam split coincidence test. So they're using what I call the chance equation. That's right. They do it right. So they did this with X-rays and assault crystal and Geiger counters. And the Geiger counters don't have pulse height resolution, but still, I say they're using the right analysis here. That's how I do it. You take the rate in one detector, the rate time of the other detector, and this time window within which you count as coincidences, you multiply that together, and that's the chance rate. Then you look at how many coincidences happen within that time window, and that's the experimental rate. And you compare the experiment to chance. They did it right. And when they do it, and a few other people did the same thing, you see that it's 1, that it looks like chance, that it only goes to both detectors at the chance rate. And that's what quantum mechanics will predict. And so they saw 1. But there are other problems. There's a list of problems. I say what's good and what's bad about these tests. So the next test that was done, it's with visible light. They dimmed it down to make the argument that it's like 1 photon at a time. And then it goes to the coincidence electronics. And what's good here is they will test the time in between pulses with a histogram of time difference. They'll insert here a test pulse that will create coincidences. And you see this great big peak that says it goes both ways. But when they do the real experiment where they dim it down, they get this band of noise in the time difference, this delta T graph, the time difference histogram. And they use the same chance equation also. So there's 2 ways of looking at this experiment, these experiments. Just looking at the graph of time differences, or looking at the ratio above chance. And it's good to do it both ways. So they understood that if you do better than chance, quantum mechanics needs to be heavily adjusted. They get it. Then it was done again. This is a very famous experiment, John Clauser, and they gave Clauser the Nobel Prize for related work, just about the same apparatus. Anyway, I call this a one particle experiment that goes to a beam splitter, but it was two to start with, and there's some explanation of that it's one at a time because they get coincidences when they look at both ways. And so that's their idea, their rationale for saying it's one at a time. And then they do the coincidence, the time difference histogram I was just explaining, and they see this band of noise again, which means it looks like it goes one way or the other at a beam splitter. You do not get coincidences more than chance. And quantum mechanics is confirmed when they see no coincidences in this kind of graph, this kind of analysis. But again, there are all kinds of problems in these tests. Visible light, like I said, has this problem making an energy budget. The pulse height filters are not explained. They don't say anything. The singles rates were not reported. They analyzed it in a different way. They didn't use the chance equation, but the histogram is here to see that, how it looks against chance. They used polarized beam splitters. Now, I have no idea how they get away with this for so many years of using a polarized beam splitter here. From other tests, and I give the references of that elsewhere, the emission of an H nu will be polarized. When it encounters a polarized beam splitter, it routes the light one way or the other. So that voids the whole test to use polarized beam splitter with a polarized light. So there are lists of problems that I'll point out with these past experiments that everybody relies so heavily on to say it's quantum mechanics. So here's yet another one, Aspe. And Aspe and his team, they won the Nobel Prize also for that related Bell test. But the interpretation of the Bell tests comes from these tests, which are more fundamental, which say that quantum mechanics and the probability interpretation is true. It comes from these tests. So here's the beam split. It's really a triple coincidence test, what's going on here. They have a source that emits two, and they can pick up if it goes opposite directions, and they're using that as a trigger to look at the other pair and then see, does it do a triple coincidence? They didn't use the triple coincidence chance equation, which was really straightforward. They didn't tell me the singles rates. They didn't tell me a whole bunch of stuff. So it's very difficult to analyze just really what's going on here. But I do understand the apparatus. And when they then go ahead and take what they say is this one at a time source, and then do the wave part of the Einstein's photon model. And that's a good part of this test. They understood that the photon model has a particle part and a wave part, and they're both equally important. So, but when you look at how they label this, it's just wrong. They say, what does it say here? Single photon input. It's just not that. It's a triple coincidence. They explain in their text, and also you can tell from this diagram. So I rewrote really what's going on here with the wave part of the test. I redrew it. And then there are all these problems, same problems as before. And they also used a polarized beam splitter. So I'm asking to go back and explore, analyze these experiments and see, well, can we see other ways to interpret what went on? They all say quantum mechanics is right. This is why they say quantum mechanics is true. It's from this set of experiments in the what I call a one particle at a time beam split coincidence experiment. So let me set the stage, try to review as to what I'm trying to say is going on here with a threshold model that predicts a 2-for-1 effect. If you set up the beam split instead as a thin detector in front of a thick detector, it's a bit easier to do the experiment and understand what's going on. So I'm using gamma rays. I'm saying that it's an h nu emitted, not a photon. We do embrace E equals h nu. It's quantized like in the first instant of emission. I'm saying that an electromagnetic wave will thereafter spread classically. So what has to happen is that there's a preloaded state. It's like cups that are partially filled. And then when it gets some amount, like Millikan's minute addition, all of it can spill over, make a detected h nu, a full h nu. And we see that. And in the other detector, a full h nu together in time to cause two detections more often than chance. So the argument requires timing resolution, energy resolution, and this assurance of single emission. We have that, and they don't. Well, I have it much better. I argue that I have all these properties better. And so here's the experiment that I do. So here's the time difference histogram, and there's this great big peak. And we're going to look at the numbers. I give all the numbers, the singles rates. Here's the thin detector in front of a thick detector. I'm using cobalt 57 that emits one at a time. Let's look at this one at a time claim. The test for that is where you sandwich the radioisotope around a pair of detectors, the same detectors that you're going to use later here. And that's what I do with the same setup, the same pulse height settings. You surround it and you do the coincidence test and see if you get coincidences. Do you get this band of noise that says it's one at a time? When it's surrounded like this and you get a band of noise, you know it's one at a time. If it was to emit two, you'd see a peak in this histogram. And this is how the nuclear physicists tell whether the atom emits more than one or what. And that's how they make all these energy diagrams of all the nuclear physics. Understanding nuclear physics is done by this test. So the radioisotope I use passes this test, and I've done it in my lab. I explained that in my previous lecture, by the way. So then we go through the pulse height filters. We get the rates in the first detector, the rate in the second detector. We take this time window, some number of nanoseconds. We put all that into the chance equation. We calculate a number for the chance rate. Then we have to do a background test. We take away the source because there are some coincidences that will happen from gamma rays from the environment. We put the source back and we see, well, what do we get? We get some count rate that is read out in the oscilloscope, the peaks and the duration of time. We get a rate from that straight off the instrument. We subtract the background here. Then we take the ratio of the experimental rate to the chance rate, the same way those other two earlier tests did. And we get 6 times chance. Here, the photon model falls. And I've done this 100 different times, maybe 1,000 times, scores of different ways. And that's different from what other people have done. You could see all the different ways I've repeated this. And so the way I do it is much better. We have the timing resolution, the one at a time test properly done, different geometries. I did it where it looked like a beam splitter also with similar results, and different radioisotopes and different detectors and different kinds of beam splitters. They're different materials as beam splitters. Now, why, you might ask, has this never been done before? Because it's pretty sensational. You'd think that it has been. There's good reasons. There are only two isotopes that have the properties necessary to see what I call the unquantum effect, to do better than chance in this test. That's the unquantum effect. So they have to emit only one gamma ray per decay. It has to decay to a stable isotope and not emit another gamma ray after it decays. It has to have a reasonable half-life. And what I use here has all those. And the photoelectric effect efficiency has to be higher than the Compton effect efficiency in the detector that we use. And so I discovered this. So this is a graph of the absorption of our sodium iodide scintillation detector versus the electron volts of detection, which is the pulse height, which is also proportional to electromagnetic frequency on the horizontal. So we're using these two isotopes in this region where the photoelectric effect dominates over the Compton effect. And that's where you get to see the unquantum effect best. Now, there are other isotopes where it's too noisy down here with the smaller pulses. You can barely see the unquantum effect. And up here, where the Compton effect dominates, let's say in textbooks, they'll give examples. They'll say, oh, what happens with cesium-137? Can you see an anomalous signature of there being a 2-for-1? No, I'll show this later. But you do not see the unquantum effect up here because the Compton effect dominates. Another reason is our best detectors, when you use liquid nitrogen cooled detectors, it pushes these isotopes over to where the Compton effect dominates more. So where you expect to see it better, you see it worse. So there's things where you just wouldn't expect. Also, who would expect to see that the most particle-like kind of light would show that light is not a particle? So that's what I did. It's counterintuitive. So what about rest mass? So that's even harder to understand. That was really the hard part in figuring out all this. So this great experiment back 1929, Esterman and Stern, they diffract helium and it conforms to the de Broglie equation. Completely great. What the heck's going on? Well, they interpret it by the probability interpretation of like particles diffract, all that stuff. Then there's this other important experiment where they diffract helium again in a grating of circular slits, and they focus the helium nuclear wave function, so saith Eric, and they see the signature of the wave. And that's great. But what's this? There's straight through, there's a signature of the particles. And the authors admit that this is a wave and particle signature in the same experiment. It points out that these rest mass stuff like atoms have two states. It's a soliton, which can hold itself together or lose its ability to hold its and spread like a wave. It's a two-state solution for matter. There is such a thing as particles, but it can lose that when you do beam experiments and express itself as a wave. So there are all these experiments with heavier molecules where they show that it calculates out to conform to the de Broglie equation. And that has convinced many people that quantum mechanics is true. These are not one at a time experiments, by the way. There's a flood of these molecules, giant molecules going across space, and they can interact with each other. And the molecules can interact with the diffraction grating. It's a simple enough experiment where you can do calculations on this. They give the dimensions, and I've done the calculations in another paper that I published to say that things don't fit by the calculations by the diffraction. And I've used this simulator, and well, the pulse heights and the widths and stuff, they don't fit what their experiment shows. And they try to weasel around that by saying, oh, there's van der Waals forces interacting with the slits. But that's a particle model of the particles interact. So what's going on here? I give a few ideas as to what might be going on. But what I think is going on is that they're looking at a shadow pattern, and that the size of the pattern is focused by the electric fields of the slits. That's my take on it. And so I confronted these people with that idea, and they dismissed it out of hand. We'll see how they respond to me later, or how people talk about this. I don't expect all this to be figured out right here in this lecture. People are going to be arguing for a long time over my challenge to quantum mechanics. But I do this experiment with helium, with the alpha ray, the helium nuclear wave function. It's similar to what Rutherford did, bouncing alpha rays off of a gold foil. And so we have alpha detectors behind, it clicks. We have pulse height resolution and timing resolution. It's the same experiment as done with light, except I'm doing it with the matter wave now. Some of the alpha signatures will go reflected. And well, what's going to happen here? Is it a 2-for-1 split? If it is, it's not a probability wave. The probability wave would say it would go one way or the other, but not both. So we're testing that. What if we see half height pulses, like 2 deuterons, a split from helium? Well, that can happen, but it takes more kinetic energy. It takes 14 MeV to do that split by other people's experiments that are published in their theory and everything. But I only have 5.5 MeV kinetic energy as the known kinetic energy from the decay of this isotope. So let's see what happens. The data is, I went to great pains. I did this experiment over and over, rebuilt the whole thing several times. The pulse height histograms for each detector is on the X and on the Y pasted in carefully to see, well, what's going on here. And I programmed my LaCroix oscilloscope through quick basic to see everything. A lot of work. So most of the coincidences are half height. And when you calculate out it was 100 and something times accidental chance in defying the binding energy understanding of what an atom is, which is pretty important in itself. But up here, we have a greater than chance, depending on how you do it. I wrote 6 times chance here. Great. It's well above chance. Anything like 2 times chance is sensational. Anyway, we're way above wondering, am I looking at noise or anything? And also, I did the 1 at a time test, and I could see that that worked. They know that it emits 1 alpha ray at a time in this radioisotope. And here's the time window I used. So we're getting 2 for 1 from the atom, splitting the atom like a wave and showing it's not a probability wave. The matter wave can split, and it's loading up helium into everything. It's saying everything has heliumness in it that gets to load up to a threshold and show itself as helium. That's my explanation of this experiment. I'm sticking to it. So going back, I'm talking about myself. I've been unashamedly inserting myself into the history of physics. Please bear with me. So the other people, they don't have pulse height resolution. They don't show what their pulse heights look like. I show everything. All the pulses are well behaved. The histogram of pulse heights is all displayed as to what I'm using. And their data looks like noise, and mine looks like something happened. So that's the comparison where I stand. And what this ends up with is that there is no entanglement. There's another way of seeing. There's no ghost wave. The measurement problem is solved. There's no superposition. There's no quantum weirdness. With a simple idea, well, I have to explain how do you see this to really make it work with a model of thresholds and ratios. I'll explain that in a few more slides. But first, Einstein argued against the probability, the quantum mechanics. And I stand with Einstein. I stand with Schrodinger and a few others to say there's something wrong here. So they do these tests, and they really mean it, saying things like, well, is the moon there if nobody looks, kind of thing. This is kind of interesting. You can tell the kind of detection they use, that they're looking ahead of the kind of detector, but they're not looking at this idea of a preloaded state as one of their hidden variables, which means Bell's analysis was incomplete in that way. I'm saying that's what's wrong with Bell's theory. And I've already explained what's wrong with quantum mechanics. But anyway, these people are emphatic. They say they have to abandon realistic, anyway. This one is good. What bothered Einstein is not a debatable point. I'm debating it. I'm standing with Einstein. Einstein was a complicated character because I argue against the photon model, but then he redeemed himself. He got it right later in 1935. So in the meanwhile, they gave the Nobel Prize for this, for experiments with entangled photons. They're saying, oh, yeah, photons is a done deal. Well, here's what the early experiment was done by Friedman and Clauser. the experiment comparing the Bell, you all know this. I'll just say it anyway. That the relationship between the angle of polarization in a coincidence experiment will be a curve as a function of angle on the horizontal and the number of coincidences on the vertical. Bell's theorem predicts a straight line, and this is where they say quantum mechanics does not conform to Bell's theory. But I'm saying, I already pointed out, well, there's probably something wrong with Bell's theory. It's important to understand here this curve that the experiment and quantum mechanics and the law of malice, the classical understandings all agree with this curve. It's only Bell's theorem that disagrees. So what do I say is really going on? I have some derivations which are useful. I derived in a connection between the photoelectric effect and the de Broglie equation, and using Schrodinger's beats idea to get this factor of 2 equation, and it's like a derivation of the de Broglie equation, which is in here right there. So you could do this backwards or forwards, starting with the photoelectric effect and getting the de Broglie equation, either way. But it's a connection between those two ground floor understandings of physics, those two equations, to relate them to each other. If you take this as a derivation of the photoelectric effect, it's a much better derivation than what Einstein did, which is a cram together of what's in front of you and say, let's use the particle model. So my derivation is algebraic. Then there's the derivation of these and understandings of these other effects. But what are these little m's and h's and e's doing in the equation, which look very particle-like? Here I am saying it's a wave derivation, but there, let me explain how to fix that. If you look at the experiments that are famous for the wave effects amongst physics, you'll find ratios that describe the experiment. This would be the electron diffraction experiment. This is the de Broglie equation. So all I'm doing here from the left column to the right column is rewriting the ratio as a Q and saying the message of the experiment is the ratio, and saying what is nature telling us without the particle model. Nature is telling us that when you have wave effects, these ratios show up in the symmetry amongst our equations describing our wave effects, all of these effects. So let's take the case of electron diffraction and look at a picture of what am I talking about here? Let's take an electron where there's a charge mass and there's an action associated with that amount of energy. It's initially like a particle, then it spreads in a discontinuous event, spreads like a wave. It smears all over the place. It smears out. But I'm saying take a cubic volume of that matter wave and see, well, what charge, mass, and action is in it, and say, oh, there's less charge. It started with a full E, but it's only a small amount in the E's and M's and A, in some sample volume in space in the charge wave. And then realize what's going on is that the ratio is conserved. This is the trick, the way to see through wave-particle duality. And this came first. And after I realized this, I knew to go to the experiments to test it. the theory predicted the experiments that I do. Please go back to this. It's a concept that most people just do not get straight away about this principle of conserved ratios. And so, all right, I did the experiment all these different ways, different detectors, alphas and gammas and so on. You could see that in my other lecture. And then this is the easy way to do the experiment, the unquantum effect, with one detector, and look at the pulse height spectrum of cobalt-57 with a 3-inch detector of sodium iodide, and look at it in the logarithmic scale, and examine the sum peak, which will happen if there's 2 of these larger, it's a much larger pulse here. I drew it linear in the linear scale. This is linear and that's logarithmic. If there's, you count the rate. Here I counted, 20 bins. How many happen per second in the photo peak? The pulses superimpose with flashes of light to make light flashes that are twice as big, to make bigger pulses that show up here. That's what this is in the twice high part of the spectrum. Horizontal is pulse height. And you count how many pulses are here, what rate. And then you use the chance equation, just like pretty much like before. It's a slightly different equation. You use the rate squared. There's a factor of 2 in it. There's a time window. The time window you get from, let's see, what was it? It's in other people's analysis as to how the light flashes. So I took 300 nanoseconds for the time that the light exists in the scintillator. And so this is a conservative number for the time window. So you calculate out what the chance rate is. And then you compare to the experimental rate, the rate read here in that sum peak, and I get 6 times chance. Very easy to do. You see the unquantum effect with one detector. And so if you're going to argue with me about what's going on, you can do this and argue with the experiment and try to see, well, what's going wrong here? The experiment that says there's no entanglement. And this stuff about quantum computing, if you're relying on entanglement, you may want to think about it in a different way. That's what the results of my work here. It's all on thresholdmodel.com. And I'm ready for questions.
Great. Yeah, there's a lot of questions. Maybe we could start from the top. So I guess, well, Terry had a lot of questions, but, well, I don't know, Terry, do you just want to ask those questions in person right now? I see you on video.
Am I on video? I can't tell from this end.
Yeah, you're on. Yeah, you have your video on.
Yeah, I made a number of comments. Well, I will ask one specific question. This very last one, I'm completely missing the point about the unquantum effect with gamma rays. Gamma rays are not usually used to study entanglement because they would be extremely difficult to entangle in the first place through the high frequency.
Yeah.
So what is your point?
That's what the whole lecture is about.
The whole point is that entanglement shows up when you set it up at levels at which it becomes significant. If you simply go into the domain in which it doesn't apply, yeah.
Well, It's just funny to me.
Do you not care about the domain in which it actually shows up? You only care about the domain in which it is.
I'm doing the experiments by which we understand the probability interpretation of matter and light. I'm playing by their rules.
Okay.
Playing by your rules.
Let me ask you a different question. Where do you get your preloading? The reason that Schrodinger abandoned this whole idea is it doesn't work. You can't have infinite loading from an infinite number of sources around the universe. It takes an infinite amount of time. So
no, it's not like that at all.
The continuum doesn't work. You said the continuum doesn't work. You agreed with that, right?
What?
Okay.
That what doesn't work?
Preloading coming from?
A continuous. It's a time sense as to how you look at how it loads up. You look at the time sense of it.
Well, where's your preloading coming? You introduced an idea of preloading. Where's the preloading coming from?
It's inspired by Millikan's understanding of the photoelectric effect.
Where are you saying it's coming from? This is your theory. So where's your
preloading? Well, it's inspired there, and I address it both experimentally and theoretically.
But so if you do it experimentally, you simply wind up replicating quantum theory.
No, I'm not. I'm showing the opposite of quantum theory.
Then where's the preloading coming from?
It comes from all kinds of noise that we're made out of. And it's a dormant state. It's not that hard. It just doesn't show itself until it reaches a threshold.
I'm looking at a star on the other side of the universe, galaxy side of the universe.
Don't give me the other side of the universe stuff.
Well, I can see.
I'm sorry. I'm going to have to let you go. I'm not going to explain with other sides of the universe.
But you said it was preloaded. You said
yes. It's preloaded from the way everything works.
Well, we can see those. I can look at my front. I can look at my front door and see the Andromeda galaxy. Am I preloaded for those?
No, it's not like that at all. I don't know where you're getting that.
Well, no,
I'm tired of arguing with you. I want somebody else.
Okay, then explain why you're splitting helium for no reason too. Later.
No, wait. Other people have shown the splitting of helium. I gave good background for that. It shows wave properties. I did a good experiment. I'm not going to be dismissed so easily. When I give decent experiments.
Helium, undoing the helium diffraction.
What?
Levels aren't there. Nothing is there. There's no deuterons there. You'd be radioactive all over the place if there was.
What would it take to split helium into two deuterons? It would take energy. It would take more kinetic energy than what I have.
So what does that have to do with the helium diffraction experiments?
That I'm getting 2 for 1. We know about the wave properties. We can explain it with probability, but I'm defying the probability interpretation by all this history of physics to show that it's not going one way or the other. It's not holding together like a particle. You can get a loading going on. I'm showing 2 for 1 where either you give up energy conservation altogether or you look at the loading theory.
Okay. Now, actually, I have to admit, I'm genuinely confused. Are you actually saying that splitting the helium into 2 deuterons is part of the process or is not?
I'm not.
I'm
saying it does not split into 2 deuterons. I do not have the kinetic energy to do that.
Right. And we're in total agreement.
Yeah.
With that part.
Yeah, it's not 2 deuterons, but there's a signature of half height pulses. That's part of, let me go to that slide. That's part of the experiment. That you see a lot of half height pulses, but it's not, that doesn't explain everything. It's these full height pulses that are the stronger result of the experiment, that I defy chance by getting full height pulses. The pulse height is known from many experiments that it's proportional to the kinetic energy of the helium. So the pulse height and the coincidence rate tells you what's going on. And it ends up being a 2 for 1 kind of result that I'm analyzing in the same way other people looked at these beam split coincidence experiments. I'm doing the same thing the same way other people have done these experiments. But I'm the only one to attempt it with gamma rays and the only one to attempt it with alpha rays, and I get the opposite answer.
And we will get exactly the same discussion I just had a minute ago, that you're going into the domains in which the diffraction effects will be minimal because of the energies involved. So, I mean, this just goes in a circle.
Minimum because of the energy involved.
If you're using, what are you using? You're using radioactive emissions. Are you expecting diffraction? I'll leave that. I'll let you get questions.
I don't think you understand what you're saying about the energy involved. I know what the energy is. I'm reading it in the experiment. The pulse height says what the energy is. Everybody understands that the pulse height is a signature of the 5.5 MeV of the alpha ray click, the click that happens. So I don't know what you're talking about lower energy.
No point in repeating the same points.
All right, next question. Next person. Thank you. Thank you.
Well, thank you, Terry, for the discussion.
You're welcome.
Just gonna move on to some other questions in the chat. Yeah, Eric, somebody asked, so are all differences is discrete versus continuous?
All differences. I couldn't get what you're saying. Discrete versus continuous. There's a continuous property that we're acknowledging. Straight away, we know that from diffraction, that particles don't diffract. That's the first step. How do you understand, how do you explain the particle properties is what I'm doing. We see the wave properties in the second half of Einstein's photon model. What's the particle property? Does it happen like that as one way or the other? Or is there something wrong with the experiments? So I'm addressing it all throughout history as what this wave particle problem is. Looking at how they develop the ideas in relation to experiments, showing their experiments, pointing out possible flaws, redoing the experiments in a completely different way that you can see does not have the problems of other people's ways of doing things, and getting the opposite answer. So what was your question again?
I don't know. I think that question was Itamar. Itamar, are you in the Zoom room right now? Did you want to clarify on your question? I guess not.
Yeah.
Okay, well, moving on then. Somebody else asked, how many quantum effects can we use today can be described by your theory, for example, tunneling effects?
Quantum mechanics usually works. If it's going to take a long time to go over the last 100 years of experiments and analyze them in a way that includes a threshold. You see, the threshold model includes the idea of seeing things as if it looks like a particle. The discontinuity is included in the threshold model. But if you look in the way I'm showing to do it, you can see through the illusion of everything being purely quantized and particle-like, that there's this preloaded state that exists that easily explains the wave properties. So, of course, all these other experiments, many of them are done right, but we can put different words around them to explain it. Very similar to my example of what happened with the Compton effect. The Compton effect is explained with a particle model, but there's a wave model to go around to come up with the same equation. So there'll be a lot of that going on in the future to see, can we see things in a different way without pure quantization? But still, quantization will usually show up and explain everything. Quantum mechanics usually works. I'm saying how to get through the problem of wave particle duality and entanglement. I think I answered.
Right. So I actually just saw Sebastian join the meeting room here. Sebastian, you actually asked this question and you asked other questions as well. Did you just want to jump in the meeting here and just ask yourself?
Yeah, I can ask. Sorry for my noise from side, but
No problem.
because I cannot understand that you know, you can explain one effect, two effects by classical things because they can be seen by classical. Yes, like we can say that we have helium atoms could be described by Bohr rule
I'm having trouble
and quantization. And but why we can do you can describe in your theory a tunneling effect, because you use your computer, yes, and your computer use quantum effects to connect to everyone. Could you explain that this is not quantum effects, this is something else?
I just tried to explain that. Most everything is easily explained with quantum mechanics. I'm not saying to throw out all quantum mechanics. It's not like that at all. It's to explain some hidden extra properties that make it look like we're in a world of ghosts. And so it's not ghosts. There's something else going on. So I think that's what you're getting to.
It's not ghosts, it's mathematics.
No,
it's described by pure mathematical
no,
things,
it's not
ghosts.
No,
yes,
stop. It's about relation to experiments.
One thing, Eric, one thing. You cannot
What?
scream on me, okay? Because at last time you scream on me, at present, no, okay?
Who is this?
Because this time I'm not a moderator, but if you can, don't scream on me, okay?
It's about relation to experiment, not theory showing you what's going on. I'm very close to experiments. If you're going to try to explain to me in terms of theory, you're going to hear me backtalk. Oh, I'm sorry, I won't do that anymore. Go ahead.
Yeah, but no, it's not me neglect quantum theory, but you, and you propose new kinds of theory, which is not quantum.
Right. I'm proposing new kinds of theory that is not quantum in relation to experiments. Look
yeah,
at
but quantum
experiments.
theory is related to experiments.
Yeah, I know. I looked at those experiments. You can re-examine those experiments. I show how to look at them. I'm not throwing away altogether the experiments. There are many experiments that'll show the discontinuities. We know about them. There are experiments that'll show the wave properties, experiments that'll show the particle properties. It's been interpreted by a probability interpretation and the mathematics of quantum mechanics, but it leads to entanglement and conceptual difficulties of ghost waves, and it leads to a result of experiment that's different from my experiment. So I'm showing the distinction experimentally between quantum mechanics and a threshold model.
Yeah, but can you tell me, we have quantum mechanics from more than 100 years, and we have a lot of experiments. Wait, but can you tell me just one thing in your theory that is better, or I don't know, you better compute some constant which you can compute from quantum mechanics, and you can measure, or you can do, because we derived 1,000 of experiments, 1,000 of things. Your computer is made because of quantum mechanics, yes? So why you neglect it? Yes, because it works, because someone choose quantum mechanics and describe this by quantum mechanics. So why it's so strange? But the strange is that you cannot understand it in classical way. By classical, I know what I mean by classical. By classical, you mean mathematically is points and waves. And quantum mechanics exactly say that no, it's not points, it's not waves.
I know all that stuff. We all know all that stuff. Particles and waves. That's the paradox. Is there a way to see what's going on? They give up from the very beginning. The model of quantum mechanics is to say, give up. Don't even try. Shut up and calculate. Well, I'm not alone in saying, well, maybe there's something that could be seen besides that. So I'm revealing what and how to see it. And this is really wearing away on my nerves. So I don't know how much longer I can take it.
I can agree with one thing, that everyone wants explain what is going on, yes, but we know that if we are going to the classical way, it will be not good, yes.
I'm not doing classical.
Yeah, you do it classical.
I'm doing in an understandable way.
It's this understand way is classical. It's the same like changing point of view that Copernic and helium and other kinds of thinking about is round, it's sun round or earth round. It's the same. You say, okay, let's back because you see it in wrong way. But your model is classical, and you cannot say that it is not.
No, it's not classical.
Yes, it's classical.
There are extra properties that I'm pointing out. And if you see those properties, then you can make sense out of the wave properties. And this argument is not going to be resolved here. I'm not going to just stay on here for the rest of the session and argue about it. People are going to be arguing with my results for a long time. And they're going to do it and see, well, did Eric show something? You're going to find that Eric showed something. And they're going to look back at people like you and all right, I'm going to have to stop.
Can we ask other questions, please? Can we ask questions? It's interesting to listen to the debate, and I would like to show appreciation to Eric for your talk and your courage and to challenge the establishment. It's important to challenge establishment. So your theory has got its merit. So I'm not an expert to confirm that you're right or wrong. I have some few questions to present to you. One of my few questions is about entanglement. It will appear that you're not accepting the current theory of entanglement. And I just wonder, there are companies around the world and institutions and governments working on communications. And they're using the theory of entanglement. So I wonder if you could explain this communications, quantum communication, based on your theory of preloading, and also if there are limitations in terms of distance for communication via entanglement or preloading.
Yeah. Well, I've looked at those papers and explanations, and I tell you, it all looks like quantum propaganda to me. I just don't believe it. I expect that when people look deep into what they're really doing, they'll see through some kind of doublespeak and see that it's the theory ahead of the experiment that they're pushing. So I haven't really seen the quantum entanglement or the computing work. They make all kinds of excuses around it, and there's noise problems. I mean, they're saying that quantum computing is going to figure out how quantum communication is going to work because it hasn't worked. Well, just look closer at the claims that people make, please, and see if it's really true. It doesn't look true to me. So I know what you're saying. Everybody says it works. So we'll see. Who's next?
Fine, thank you.
Great. Yeah, George had a question. He says, thank you. The history is fascinating. Any thoughts on Poincare's 1912 proof of the quantum discontinuity of nature? I don't have the exact reference handy, but there are secondary sources.
There is a discontinuity. That's what it's all about. I'm not familiar with that paper, but there's a really great book that I refer to quite a bit by Thomas Kuhn, Black Body Theory and the Quantum Discontinuity. So I like to refer people to Planck's second theory of 1911, which is on my website, about the discontinuity, that there's a way of seeing it where the absorption is continuous and the emission is discontinuous. That's the discontinuity. The discontinuity is true, but it's not true in absorption. Absorption by Planck's second theory and by experiments, my experiments, shows that the absorption can be an arbitrary loading up. See? So it's a difficult illusion to see through, the illusion of quantization. You have to be really tricky like me to understand how to adjust the experiment to see through the illusion. Yeah, we know about the discontinuity. Did I answer?
Yeah. Hey, George, are you in the Zoom meeting? Did that answer your question? You could unmute. No worries if you don't want to.
By the way, could I ask a friendly question to Eric?
Hello.
Eric, I just want to understand what is I'm not sure if I understand fully what your main premise is. I think it is this preloading idea. Is that correct?
That's a big part of it, yes.
Okay. So can you explain the preloading as much as you can? I realize that I think for you it's something that you see as a possibility but not fully expanded. But can you talk a little bit about because the preloading is not in the original Schroedinger idea, right? The preloading is your own idea.
Right. Well,
yeah, but just can you explain that a little bit, because I'm trying to understand what your concept is there, how that works. I get this idea of like the cup's almost full, preloaded.
Yeah, let's go to the cups.
Tipped it over, and I can understand that. Yes, that's a good figure. I understand what that's going on. So, but you're saying more broadly than just for electromagnetic.
Right.
Could you
To resolve what's going on must be about both matter and light. The matter part was the hard part. People have already explored the idea that the photoelectric effect could be done with a quantization in the absorption and emission. The matter part is best explained in this slide with the principle of conserved ratios, where the identity of what goes across space in the matter wave is in the detail of the wave, such that what gets absorbed continuously can pick up the signature of the matter wave. Like with an electron, the signature is the charge to mass and action ratios are all staying in proportion, a property of the wave. With the alpha ray, it's similarly with different charge and mass into those terms to start with, that the ratio is conserved in the matter wave and then loads up to a threshold. So it's just as profound to say that there's a threshold effect as a quantum effect, but I'm adding this extra detail to see how it could work to explain the wave properties without this entanglement from both sides of the universe stuff. It's not necessary. You don't need a probability wave. So I don't know if I explained it well enough.
One question that one. You have an E, an M, and an H. E is electric charge. I assume that's what you mean by E
Right.
when you electric charge. What about
What about M?
what about neutrons? If you send a neutron, there's no electric charge.
Oh yeah, right. Well, it won't be E, it'll be zero there, but there'll still be a mass and an action. There'll be a property of the wave that you fill in here. And there may be other properties of the wave, but I'm giving a good starting point and how to connect it to other experiments to see this symmetry in our equations that have these ratios and how to read the equation of these experiments where it's not necessary to be quantized to show the wave effects as to what goes across space because of this ratio of the property of the wave that gets conserved. It's an advanced concept. I don't expect people to pick up and understand this right away. This was hard to figure. But
for whatever it's worth in the volume concept, that actually is not a difficult. If you take the product of the Lorentz contraction by the time dilation times the volume of the unit, you get an invariant volume. Oh, it's not that painful. You can handle it.
I don't understand so far. I'd have to
what I'm saying is
dig into that.
The reason I'm familiar with the concept of an invariant volume is there's an invariant volume in special relativity, although it's not commonly portrayed, but it's just that every object has a volume that is invariant in four-dimensional space for all observers, no matter how you look at it, which is just interesting. But it's saying that there's a conserved volume and that volume persists. And I think you're saying something a little like that, maybe?
No, I'm not saying the volume persists.
Oh,
I'm saying the wave spreads, and to look at a little piece of the volume of the wave that's spreading and look at the property of the wave.
Okay, so you're saying well, that's why I'm glad I asked that then, because I thought you were talking about a distorted volume that was okay. All right, that helps me understand what you're trying to say.
Thank you. Very good.
Thank you.
Great. So moving on to another question. Neil asks, Eric, does the threshold model suggest that energy can leak out of a preloaded atom?
Yeah. Well, I don't expect to be able to suck energy out of nothing this way. It's still going to have to load up to thresholds to express itself the way we see in all of our experiments. There is such a thing as what I say, a preloaded state smeared all over space. It may explain the dark matter, by the way, that there's something there. And what was your question again?
The question was, does the threshold model suggest that energy can leak out of a preloaded atom?
Leak. No, I don't expect it to leak. I expect that it only expresses itself when it reaches the threshold to give emissions. And that's the way our experiments show everything works.
Right. So, Neil, I see that you're in this Zoom meeting. Does that answer your question, or did you want to clarify? You could unmute.
Yeah.
Yeah.
Can you hear me okay?
Yeah.
Yeah, I just say I was thinking that if the I understand that the theory is that the atoms load up by a frequency dependent effect, so they can load up with energy. But if it doesn't leak out, then in effect, atoms will accumulate energy at whatever the resonant frequency is and not leak it out. So it'll be like a kind of one-way thing until they reach the threshold. Is that right?
That's what it looks like, yes.
So in effect, atoms are just harvesting energy out of the environment at whatever their resonant frequency is.
That's what it looks like.
Okay, thank you.
Good. That explains, well, how do you get this preloaded stuff? Very good.
Yeah. Yeah.
Great. So that was all the questions in the chat. Yeah, wow. Interesting discussion. Did anybody else want to unmute and have any other last minute questions they wanted to add in to this meetup here? Anything?
I'd like to ask if Marco is out there or if David Chapman is out there, two fans of mine. Probably not. All right. Thank you.
Yeah, I don't think I see them in the list.
Yes, David Chapman just joined. David, do you have anything to add? Chapman.
Yeah, Dave,
Question very quickly. Is the preloading, or does the preloading affect the particle spin?
It might be. I ask you to elaborate. I'm sure there's all kinds of interesting physics to do connected to spin. I did do some work on spin, but I'm a bit anxious on elaborating right now. But it's on my website as to how I handled spin in counter-rotating psi waves and such. And
I was asking this because going back to this debate about entanglement. So if the particles they appears to interacting through the spin, and then if you're rejecting the current theory of entanglement, so how could you? Is it possible to explain it through the preloading? That's kind of question that I'm trying to elaborate.
Well, I don't know of an entanglement done. I mean, I see people explain it that way, but I've never seen it done that way. So I asked to go back to real experiments and not thought experiments to start with.
Yeah, but you can define what is spin for you, or you cannot.
Well, I'd prefer not to get into spin. I've done, like I said, some work
So
on spin.
it doesn't exist for you.
What?
It doesn't exist for you. Spin.
No, it plenty does exist. I handled and worked on spin, but I'm not prepared to go into it right now. I'll refer you to my paper of an understanding of the particle-like property of light and charge that I posted on my website and a few other places. So I do have a theory of spin. I did some calculations of atoms entering the Stern-Gerlach magnet and what it's about. I'm just not prepared to go into spin right now.
Eric, could I ask another question?
Yeah.
First, I want to point out that there's a paper of yours from one journal that I went ahead and posted in the chat.
Thank you.
So in addition to the ones on your site, so if people want to see one that's published independently of your own site, they can go to that. I think that's the one on wave particle duality entanglement. So that could be useful in that. But what I was going to ask you, when I went through your experiment, actually I've gone through your stuff in quite a bit of detail before this meeting. When I see your experimental parts, I know to you this seems very strong and that you've got a solid thing, but I'm not quite getting what is the just the critical part that you feel disproves something that was seen before. Could you elaborate on what would be the single experiment you have in some of your stuff that to you most captures a deviation from what's expected?
It's about comparing to chance in the beam split coincidence experiment in this whole history of other people that have done a similar experiment. It's about doing better than accidental chance as to what happens with clicks past the beam splitter. I'm doing it the same way they're doing, at least for these 3 tests. Actually, all of them. They'll describe it a bit differently in their theory.
And I think where I'm getting confused now is I'm looking at that, but I keep seeing it as everybody is still finding one particle in the end, or am I?
Yes, I'm doing it in a similar way, except I do it with gamma rays, and I'm getting the opposite answer.
No, say that again. Which part of it is the opposite of the answer? You're both getting one. Everybody winds up with 1 unit, 1 particle at the end. The opposite answer in the sense of, just elaborate the word opposite as you just used it.
2 for 1.
2 for 1.
Right. You start with 1 on the source. You end with 1 on the detectors because you think it's quantized. But what if you start with 1 at a time and you end up with 2 at a time? It's 2 for 1. It means it's not quantized.
Oh, you're saying that you send out nominally 1 photon and you detect 2 photons at the other end?
Yeah, except I don't want to call it photons.
Well, two detections. 2 detections.
Correct. Yeah.
I'm okay with it.
Good.
Within what kind of a time envelope? Is it a very tight time envelope or a lot of detail here? I'm trying to pick out.
The detail is all written out. I give more detail than the other people's experiments. There are many experiments where they don't say within which the time is that you read coincidences. Anyway, in this print here, it's 300 nanoseconds. So what you do is you look at the histogram and you could just choose how you want to do this. And I've done it many different ways. You could take full width at half maximum if you want of the time window. And then you use that time number, that number of nanoseconds in 2 places. You use it in the chance equation and you use it in how many you read within that time window. And then you see, do you do better than chance in this fraction? The experimental rate divided by the chance rate. And the previous other tests see that this fraction is 1, which is what quantum mechanics predicts. I do it with gamma rays. I show everything and I get better than 1.
You get 6 times. Yeah, 6 times.
That's it.
So you have a random radioactive source. You have a profile for it, though, a good profile. When you run through the stats, you're getting levels of receipt of gamma rays that don't fit into the model of what you're expecting to go in that. So you're getting 2 for 1.
Yeah, it's a poetry thing saying 2 for 1. I embrace energy conservation.
But it's also a violation because, okay, now I think I get what it is you're saying that you see in your results that you feel is in violation of quantum mechanics. It still conserves energy, it still conserves particles, but the profile is wrong. It shouldn't be.
No, it doesn't conserve particles.
Well,
it conserves energy.
Total energy. I didn't mean,
Yeah.
actually, I did not mean to say that. I'm sorry. I meant to say energy. Total energy conservation.
Right.
With that. But you're seeing rates in which the clicks, the hits of what you're seeing aren't matching what you should be getting given a random profile that you have well characterized for your radioactive source. Okay, I think I get
The
Like-
source is tested ahead of time to emit and show in this true coincidence test one at a time. For each radioactive decay, it emits one H nu, except by the chance rate. And so we can see that in this experiment that's well established to understand what a one at a time emission is. And that's all important to get that the best way possible, because other people have done it with a whole list of ways, and there may be problems with those ways. But this way is more established to see that your source is one at a time.
So you're to use formal terminology, you're saying reality seems to be a little more blurpy than it should be. It's coming out with hits that are not predictable. It just sort of like, if somebody saw that, they would say, well, that's just a data error. That's a blurb. It's a blip. It's some kind of little thing. That couldn't have happened, so I didn't see it.
No, I don't know what you're talking about. It's not like that.
When you get the 2 for 1.
2 for 1, right.
Right.
We're looking at what all of these tests are looking for when they compare to chance. That's what would be the opposite of the result of their tests.
Right.
Would be 2 for 1, but they see 1 for 1.
Most people would see the result. If they saw 2 for 1, they would think it was a data blip, a blurb, and they would discard it.
I know. They would think that there's something wrong with the experiment because it doesn't fit quantum mechanics.
All right. Okay, I understand. By the way, my last comment. When you say that we need to get beyond the equations that we have, the things you may not phrase it just like that.
No, right. I don't phrase it. There's extra ways to read the equations.
Yes.
To see the meaning of them.
Well, I just want to say I would very much agree with the idea that we have to break through some of the assumptions that, this equation, that equation is perfect. There's got to be some underlying infrastructure sometimes on how these things are working. And if we don't try to poke at that, it's very hard to make progress. So if you just assume everything is a probability curve and that's the ultimate reality, then you're not going to go anywhere because you've already determined that's the ultimate reality. So it's a self-defining loop at that point. So does that make sense?
Yes, thank you. Very good.
Okay, thank you.
I have last question. What if you are wrong, Eric?
What if I'm wrong? Right, I know. That's been the last 24 years of my life. What if I'm wrong? That's why I've done the experiment over and over hundreds of times to see if I'm wrong, to test, well, what if it's this or that? There's a whole list of artifacts I've looked at to see, well, what if I'm wrong? I'm hip. Like, what if I discovered stimulated emission? Like one gamma ray stimulated another one on its way out of the radioisotope. Well, I did calculations on that, and I did a test for that to set up a line of radioisotope to enhance stimulated emission, stuff like that.
Yeah, but there is difference between see something and describe something. Yes.
Yeah. Look,
Yeah.
I looked for
you can see something, but your describing is totally baptist for me. So
look, there are many kinds of artifacts that one could expect in this kind of experiment. I'm trying to give the idea that I looked and tested and also looked at the theory, let's say, of stimulated emission and eliminated these artifacts one at a time. I did work on that. And I did the experiment over with different isotopes, different gamma rays, and different detectors. I showed you this whole list of different ways I did the experiment to see what makes this thing tick under different conditions. Like if I change the temperature of the beam splitter, what happens? If I put a magnet on the beam splitter, what happens? If I change the chemical state of the cadmium 109, what happens? I did many things and it made sense. So it's about looking back and seeing, what did this character do? It's not a simple one experiment thing. There's a lifetime of experiments, I'm explaining that we're behind this. It wasn't a simple thing to have the confidence to come ahead in front of you and say, the whole mess of you are wrong about quantization. It's a hard thing to do.
Yeah, but you know that there is beyond of you. Yeah, you are great. But beyond of you, there is 1,000 of physicists who
Of course,
makes not only theoretical point of view but also experimental.
of course.
So if you are say that Allen aspect experiments are wrong, show me that they are wrong. Yeah, because they are reproducible. They are
That's what
reproducible.
I know.
Your
it's just
experiment, I don't
reproducible.
know if are reproducible because you cannot describe it in correct manner that people describe something like this. So,
well,
so you see that, okay, you're great, you do your job, and you can think about yourself, anything, but you know, it's a kinds of entanglement that you are not alone, but you are in the community of physicists, yes. But for you, of course, it's statistical illumination.
Look, I went out of my way to show the experiments that look like I'm wrong. I did that for you. I'm helping you along by showing you those past experiments. So maybe you could see different ways of interpreting what they did and how to do it better. And by the way, maybe they reproduced their experiment, but did they do it all different ways the way I did? So I don't expect all this to be figured out right here and now, but please, I'm taking the credit of showing you those papers that will tell me, that will tell you Eric maybe is wrong. Okay? I did that for you. And I think I did a pretty good job. So you'll understand what they did pretty well just by looking at my lecture slides and then comparing it to my experiment.
Yeah, but you know, we use other thousands of others quantum experiment. We use it on reality. You use it also on your computer. So why we don't use your results? Because we don't understand it, or because we?
Look, I've been routinely ignored for 20 years. This is, I've made everything public. I'm just routinely ignored. They think there must be something wrong with what I did. I understand that. I know how people are looking at me. I've been living with it. Quantum mechanics usually works, but there's been this entanglement thing going on for so long, and I'm not the only one who says, I stand with Einstein. I stand with Schrodinger. Something's wrong with quantum mechanics. Here it is. Here's how to see through the illusion. So I don't need to hear, oh, quantum mechanics works for all this stuff in the computers. Please stop.
Yeah, but Einstein do more for quantum than
I
your
know
work.
he did. I know he did.
Yeah,
He did it both ways. I know he did that. There are plenty of theories that will see both ways. Like I pointed out, with starting with Planck. Planck's derivation of black body has been done scores of ways. And some will use matter and some will use light and so on. But to see the distinction between these interpretations it requires that one looks at many experiments to see how do you find consistency amongst all the experiments with a consistent model, not where you take turns with a wave model or a particle model. It's about what is a consistent model that explains it all. The probability model.
It's called quantum field theory.
Yeah. It's still probability.
So, Eric, one question, quick. Your experiments are made. You talk about photons, about electrons. So you are on the energy level of electromagnetic theory, kinds of. How you explain that we see strong interaction, and how you explain that we see weak interaction, which are completely defined and experimentally verified on this part of standard model. You neglect it, or
No,
you
that's not
cannot
it
say
at
that
all.
they
No,
are not quantum?
I'm not obliged to explain the last 100 years of physics. You're holding me to an unfair standard. I don't know how to do
No,
all
but
that stuff.
I just try to say you that you must understand that physics is not finished at the level of photons. Yes,
Right.
because
Physics
photons are
by photons.
photons are electrodynamics is a special kind of physics connected with quantum physics, because it's one of the main, you can derive it classically. Yes, in the second level that you have strong or weak interaction, you cannot do this, but you cannot derive strong and weak interaction without quantum derivation of electrodynamics.
Look,
What
I
is
don't know.
hard for you for this?
No, I don't know how to derive or attempt to derive all those things. I expect people are going to be looking over that and figuring out how to derive.
Yeah, but people done it.
Without,
people done it.
You don't need, in many cases, you don't need to mess with the threshold idea at all. It's not necessarily going to express itself.
Yeah, but so you see, we have quantum mechanics, which I can derive everything, and I have threshold mechanics, or how you can call it, which I can derive just your experiment. It is a good theory or not?
I do not see how you can derive the result of my experiment with quantization. It pits against
Maybe you should try
quantization
do it.
itself.
Maybe you should try do
Maybe
it.
you should try understanding what I'm doing.
No, because it's your experiment,
I'm not going to let you just push me like that. Oh, maybe I should do it. Well, maybe you should do it too.
Yeah, maybe, but I am theoreticalist and not an experimentalist.
Yeah, that's the point.
It's not
that's the problem.
It's not my experiment,
that's the problem.
But your
you don't
experiment.
Understand the experiments. Look at the experiments. Look at
if I could interject just for a moment, even on areas like particle physics, weak force, strong force, it's kind of conspicuous that for decades we still don't have a unified grand theory of particle physics.
Maybe there is no any such kind of theory, because you mean about gravity, yes?
No, I mean, no, not even that. The gravity is the hard one. That's one, but people have kind of forgotten that we never succeeded in integrating fully the weak and electromagnetic and strong forces. You have the grand unified theory of everything, but you also just have I'm getting the terminology mixed up. They tried it with the SU5 group and were disappointed and couldn't find it, but that is actually become a lingering problem that no one has ever resolved.
Yeah, so, but in the SU5 you have more kinds of.
Everybody had really high hopes that SU5 would just magically include.
Yeah, but you see, SU5 is natural way that in quantum manner meaning, yes, that you suspect that lower groups with lower dimension are subgroup of some higher dimension, and they check it. This is natural. So for SU5, you cannot agree with experiment strictly connected with proton, yes, the time life of the proton. So it's verified that cannot be a good theory, yes.
Oh yes, no, that was exactly.
Yeah, this is normal way that, but you cannot derive SU5 beyond of quantum mechanical description by quantum field theoretical experiments.
Yeah, my only point was that even what we have right now is not as well integrated as we kind of say it is, because if we can't integrate the clearly bosonic forces, forget about gravity, we haven't got the other three integrated yet. And I always am surprised that people used to give equal discussion to both of those. So the grand unified theories and just the theories of everything is the one in the gravity. Grand unified theory, I think, is the one that's supposed to unify the bosonic forces.
Yeah,
that's strange.
But at present, you can say that we have standard model, and this is our unified theory. Yes,
This
of
is
course, this
becoming
is
personally
this
debate
is
there, guys. I
okay.
think that we want to ask questions to Eric there.
Sorry.
And one of the questions I want to ask you, Eric, there is about verification and validations. You've been working for more than 20 years in this area. And I
Right.
just wonder if other scientists all over the world, if anyone has been trying to replicate your experiment and also trying to confirm your theory.
Yeah, yeah. I wish there were more. There is one. There's a friend of mine in Finland, and you could see on my websites or my videos that there's a video about him, and he has reproduced my experiment, but I haven't heard much from him lately. I don't know what got stuck in his ear, but we'll find out later.
But
In the meanwhile, it's very easy to do the experiment that I pointed out with one detector. You can do it. You don't need to wait for somebody else to do it. So I've been making everything transparent for all this time to show or to offer to help how anyone can reproduce the experiment. So
yeah, but there is a difference. You don't understand that there is difference that everyone can reproduce your experiment, but you propose new theory from your experiment. Yes. How many experiment beyond of you can reproduce by your theory? I can check this question because okay, someone we can reproduce Bohr
they're holding me to a very high standard.
helium classical representation
All right, I have
of
an
the
answer.
atom.
I do have an answer. By using the beam split coincidence experiment, I've made discoveries in material science. So it's a spectroscopy. There are many things to see once you understand this beam split and how to use it. So I've taken it that far. So it's not fair to hold me to a higher standard and say, oh, have you done all kinds of other experiments? I've done plenty. I've done way plenty enough to show.
Yeah, but you see, it's
and I'm playing by their
not the
rules.
word neglect your theory, but you
What?
neglect the quantum theory. Yes,
Yes.
the word don't neglect your
I'm
theory
neglecting
because
the quantum theory
yeah,
because
so
yes, for good reason. I'm showing how it fails. I have something no one else has, the experiment to show how it fails. That's what's important. Look at the experiment. It's the same experiment that everybody else uses to
okay,
show
but
that it's true.
but you derive your experiment by pure in quantum theory and showing that the quantum theory showed you bad results? No.
What? I'm going to
Do you
the quantum theory
have you
says,
done your experiment and you try explain it in pure quantum mechanical way?
yes, that's what all of those
And
other
so
experiments have
what
done.
is difference between these results and your results from your theory?
Quantum mechanics predicts chance in the experiment that everyone else has done in the precursors with light, the other light experiments. Quantum mechanics predicts chance. When you read those papers from other quantum mechanics people, it predicts chance. That's the prediction of it. And I'm showing that prediction comes out wrong, the opposite. So I'm defying chance. It's very simple. You're overcomplicating. It's a very simple argument I have. Look at the experiments that are famous for showing quantization and the probability interpretation. The most famous experiments for this, that they laud all over the place. And the more elaborate experiments call upon the ones that I've shown you, where the probability interpretation is true. These experiments are well referenced. They predict chance by quantum mechanics. And I'm showing it doesn't do that if you do it with gamma rays, and no one else has tried that. So I have I'm repeating myself over and over. It's all there in the lecture slides. And look, we've run over 2 hours, and I think I've had enough by now.
so do we.
Good.
Could I just chip in something here?
Yes.
That
Oh, hello, Neil.
Hi, Eric. How are you doing? Listen, I mean, I hate to go over the same thing again. There's this thing where the Copernican revolution came along and it replaced Ptolemaic astronomy. That worked just great for navigation for hundreds of years. It worked just fine, but it was wrong.
The Ptolemaic epicycles.
Yeah, they worked fine. They worked absolutely fine. There was nothing wrong with them. They worked. They had huge application. This is the argument being put forward by Sebastian that quantum mechanics works fine. It does, but it doesn't have any mechanics.
Yeah,
There's
but
no mechanics.
you know,
There's a mathematical formalism which is very satisfying to mathematicians, but it doesn't explain any physics.
in my opinion, explain more physics than this threshold theory.
In your opinion, okay.
No, it's not only my opinion.
I'm not
I suppose.
I'm not negating 100 years of other physics that could be explained by quantum mechanics. You're sort of missing the point. It takes a detailed experiment to see the opposite answer from quantum mechanics. It's not going to be different for everything else. So it's a well-crafted argument to see through the illusion, to see something different, to explain what's behind it, to make what looks like entanglement.
Eric,
Yes.
if you would you say it's safe to say that your idea of preloading is more of a starting point for building a theory as opposed to a complete theory? Is that fair, or how would you characterize? How well developed do you think you have? Because if you start applying this to large systems, for example, you get into a whole slew of questions about how the preloading is allocated, how it happens.
Right.
You see what I'm asking?
Right. Yeah. Yeah.
How would you
A
characterize?
good thing to look at, and I brought this up, would be the Millikan oil drop experiment, where the loading does not show up. You get charge quantization. And there is some idea. I recognize what might be going on with that and how to look at those experiments, and that it's an ensemble effect to see charge quantization in those kinds of experiments, and to look at the surface charges of the oil drops, for example, to see how that would rally together a bunch of charges to express the godzillion number of charges that are there as a quantization, and then realize it's a different state of matter where it'll express itself as a quantization or a threshold. In free space, it's a different situation to where the thresholds, the wave properties, will be seen. So I get it. It's about looking at the other kinds of experiments in the different situations. I gave you a good starting point with just looking at the oil drop. And I won't have all the answers, obviously. Good point.
Thanks. Eric, as an observation I've seen on people who've put out a lot of data on a number of areas, huge numbers of papers, and having it out there even for 20 years does not necessarily mean people will get what you're saying. So
thank you.
There's kind of an advertising thing here. What I'm suggesting is the very fact that you have so much detail, you need to realize sometimes that is an impediment to people understanding which the point is. I had to go through with you verbally through this one chart that's up right now before I think I really started to see what your main point was. So it takes, especially if it's a different angle, there can be time to see what it is you're trying to say is the key point in your data. If you have opportunities, anytime you can, to really bring out and say, here's what I'm seeing that I don't think can be explained, and I've got it verified Six Sigma, which you've done in this, but can really hone in on that point, and then have the data as the backup, can help get a message across and something like that. And I'm just saying this is an observational thing. I've worked with a lot of researchers in a whole bunch of disciplines, And my favorite example is the paper that founded Google looked like any of 100 other papers. To this day, I could say there's no way you could have known that that paper was going to have that much of an impact. But you can't tell sometimes just from the details what's going to make a difference or not.
All
So,
right.
so far,
Thank you. What's your name? Please contact me.
name is Terry Bollinger. My website is apabistia.org.
I'm not going to know how to write that down.
Terry Bollinger. I'm easily found. I'm easily found. I got Bill Gates mad at me once, so I'm easy to find.
And I'm easy to find also. Please contact me. Thank you for your encouragement.
Okay, you're welcome.
I'd like to close it up.
There is a moderator for that.
So, are there any more questions for Eric?
A great big thank you to Helen Ma.
You're welcome. Thank you for all your support.
Thank you.
Thanks, everybody.
All right.
Thank you.
I'm going to go. God. Good job.